This presentation is on the paper Narrowing the Gap Between Serverless and Its State with Storage Functions. The authors were Tian Zhang, Fei-Fei Li, Dong Xie, and Ryan Stutzman, all from the University of Utah. The presenters are Alex Shepard, myself, and Raphael Archer. Now I'm going to talk about the motivation for why they published this paper. First, some background. Serverless computing can be function as a service, but it can also be other things like microservices. We usually seem to treat serverless and function as a service pretty similar. Serverless beats infrastructure as a service or platform as a service in terms of execution cost when we do not have too many requests per unit time. That's because for infrastructure or platform as a service, we have that fixed cost of maintaining a whole virtual machine or a program, whereas with function as a service, the function can be spun up and then it can quickly go away after the request is over. There are multiple advantages and disadvantages to infrastructure and platform versus function as a service. For example, one advantage is that of function as a service is that it is easier to code because you don't have to deal with scaling or scaling manually. Now, a drawback of serverless is that it lacks its own state. So usually it's not that great for something like a database application. The contribution of this paper is to try to get the best of both worlds. Can we get the advantages of serverless in terms of a low cost of execution, but retain the ability to use state? Because serverless lacks state and because the data is separated across the network from the compute, we have to ship from various storage systems the data to the compute, and these storage systems may not be very well optimized for the needs of the serverless system across various parameters such as latency, hard drive space, and cost. The needs of serverless may differ from the storage systems. One way of addressing that is in this paper Pocket that is going to be discussed later in the course by another group, and that paper is also cited by our paper. However, that paper does not address the fundamental fact that you still have to ship data across the network. And so the contribution of this paper differs in that we address that issue directly. Another improvement you can make with serverless is using databases, which help across the parameters of automatic scaling and fine-grained accounting. Unfortunately, databases often only give limited data access models. Customers cannot run arbitrary functions on their data, And an example that this paper gives is that SQL is inadequate for graph applications where the dependencies inside the data are too complicated. The proposed solution of Shredder runs code directly on the storage server. The paper emphasizes 4 key goals for the solution. The first one is programmability. This system is called a kernel bypass system, which means that the networking routes around the default networking package in the Linux kernel. That's done to improve performance. Many kernel bypass systems only accept small and simple requests. However, Shredder is able to accept code that is more general purpose. The code is written in JavaScript that is going to be executed. It runs on a V8 system written by Google. It's a JavaScript interpreter. And the next goal is isolation. These V8 interpreters are each assigned a core, and so clearly they're separate from each other. They can also keep each tenant separated by separating the state and the code of each tenant. The next goal is high density and granularity. Now, by high density, we mean supporting thousands of tenants. And by granularity in this context, that would mean using resources like storage, compute, and networking in a way that scale separately, or that is to say, decoupling the use of those resources from each other. The last goal is performance. We want to make as much of the raw performance of a storage server available to applications as possible. One aspect of performance that they measure in the paper is throughput. And that's also affected by what they call CPU scalability, which is the effectiveness of parallel processing. Do we make use of multiple cores effectively, or does significant potential get wasted from those cores? And that's affected by the design of Google's V8.
Now that Alex explained the motivation, possible, and proposed solutions, I'll now explain the shredder design. Here's the shredder design overview. It consists of 3 layers: a networking layer, a storage layer, and a function layer, also referred to as a storage function layer throughout the paper. Each CPU core runs all 3 layers, but the cores follow a shared nothing design. This allows the CPU cores to avoid contention and synchronization overheads. I'll go into further detail later on, but for now I'll touch the surface of each layer so you get an idea. The network layer handles network connections, protocol processing, and the requests of all tenants. The storage layer hosts all tenants' data in memory and has a get/put key value interface. Think of it as hash tables. The function layer relies on V8 runtime. This layer matches incoming requests to their storage function code and context. Here on the right, we have an illustration of the shredder design. You can see tenants make a request to the NIC, which stands for Network Interface Controller. Then the NIC gives the work to the CPU cores where it runs the 3 layers. It uses kernel bypassing to lower network overhead. Here tenants have their own storage functions that they can call. In this specifically, graph, streaming, and matrix functions. The functions then can use a storage layer, which is data the tenant has stored. If the request is a simple get or put operation, then it can just call to the storage layer without going through the function layer. Each colored arrow correlates to a different tenant, so the crossed out orange arrow shows the tenant can't use their function on another tenant's data in the storage layer. So you might be asking yourself, what is the purpose of this three-layer design? Why not something else? Here I'll explain the reasoning and the benefits of it. To start, a layered design is common because its flexibility, maintainability, and scalability. Modifying any individual part of the three layers will not result in having to restructure the whole design. Shredder's design has the goal of efficiency, but also fine-grained resource sharing. So each of the layers can map any resources to any tenant at any granularity. These resources include computing, networking, and storage. A benefit from this would be the storage layer makes it so that the storage resources need not be mapped in and out of V8 runtimes in the function layer. If this were to happen, it would be costly. A single V8 instance can only host a single thread at a time, so binding data to a particular runtime also fixes the amount of computation that can be done on that data. Another reason for this design is Shredder avoids coupling by separating storage from functions. Shredder must also be able to fluidly map network resources across tenants. One theorized option to do this was to give each tenant its own hardware virtualized access to the network card, but this is not feasible because data center network interface cards typically only support around 100 virtual functions and does not scale to thousands of tenants on a single machine. So the network layer takes care of multiplexing to ensure fairness and flow control. This separated layer takes care of multiplexing resources, and in result, it simplifies the function layer and improves scalability. All these reasons combined contributed to the design being a layered type. So as I promised, I'm now going into detail for each of the layers of the Shredder design. The first one being the network layer. The network layer handles network connections, protocol processing, and the requests of all tenants. More specifically, this includes incoming packets, remote procedure call or RPC request framing, user level task scheduling, and request dispatch. The networking layer uses kernel bypass networking, and each CPU core in Shredder pulls for incoming network packets. Let me explain this more because this can sound intimidating at first. Kernel bypass networking eliminates the overheads of in-kernel network stacks by moving protocol processing to user space, and the CPU cores essentially are in a ready state waiting for incoming network packets. This avoids the overheads of the Linux kernel networking stack, system calls, interrupts, and scheduled interactions. In result, it gives Shredder high throughput, low latency, and fine-grained control over request routing and scheduling. Essentially, the network layer spreads the load over cores with the varying users to avoid centralized bottlenecks. At the same time, this also helps exploit per-tenant locality. Now we'll go over the storage layer. The storage layer is a simple layer, with being fairly easy to understand. It consists of a single in-memory record heap upon which all users' records are allocated. Users can have records that are intermixed in different sizes and arbitrary granularities. The storage layer has no spatial segregation. This means a user's stored data is all kept together. In this way, there is no internal fragmentation between tenants' storage. Though it does have downsides such as wasting storage space because users' data is always kept together, and that block of data may be too big for any user's data without being fragmented. This storage isolation is enforced by segregating hash tables. A hash table is kept for each tenant, and that maps keys for its records to data. The storage layer uses native code, C++ in this case, for uses of get and put functions for performance reasons. Now we will talk about the most complex layer of all the layers, the function layer, or also known as the storage function layer. It is known as that because of how it goes hand in hand with storage. I will restate, this is the layer where after a request is made by the user, it goes through the network layer, and then the function the user created in this function layer is called. The function layer keeps an independent instance of the V8 runtime per core. Users are allowed to install and run their own storage functions. At the same time, it provides lightweight isolation. Tenants provide their own storage functions in JavaScript, or compiled to WebAssembly, and that function is bound to that user. Only that user can call that function from the function layer. The V8 runtime's just-in-time or JIT compiler translates functions into efficient code, and that acts as a sandbox, which is very important. Because it acts as a sandbox, this prevents one user from changing stored data of another user's. Additionally, since V8 is lightweight, it can support thousands of users at the same time. Entry/exit in and out of V8 context is less expensive than hardware-based isolation mechanisms. Because of this, it keeps request processing latency low and throughput high. This makes V8 very valuable to Shredder's design. It is also worth noting when a request is sent to the network layer to run a storage function, that function's context is used again, eliminating overheads with creating the function's environment, and the function's state can stay volatile. Continuing with the storage function layer, keeping storage and functions separate comes at a cost. Functions are expected to interact intensively with data. Transferring in and out of V8 runtime can add a significant overhead, around 196 nanoseconds per call, which can obviously add up. As well, optimizations can be limited. For example, inlining of storage access by the JIT compiler. Because of this issue, each tenant context contains logic from the storage layer in an intermediate V8 representation. The storage layer retains ownership of the physical resources that make up the records and indexes, but CSA code, or code stub assembler code within the runtime, is given read-only access to these structures from within V8. It is also worth knowing what code stub assembler is. The definition is as follows. Code stub assembler is a custom platform-agnostic assembler that provides low-level primitives as a thin abstraction over assembly, but also offers an extensive library of higher-level functionality. CSA is part of V8, and therefore, as I previously stated, important to Shredder's design. Now finishing up with the storage function layer, as I was talking about CSA earlier, the CSA version of Get implements a hashing algorithm for looking up hash tables in the storage layer. It's similar to C++ hashing function for hash tables. Using code generated from the intermediate representation, or IR, tenants can efficiently traverse the structures without execution ever leaving the V8 runtime. This is extremely efficient because, I stated before, leaving and entering V8 runtime can be costly. Now, because the CSA functions with some data-intensive operations that access or aggregate over many records, this can make Shredder's operations up to 3 times quicker. Essentially, these storage functions enable a concept known as shipping code to data, which is exactly what it sounds like. This puts computation and storage together, letting functions run directly from data, therefore ultimately saving time. As for a final note, a user can use JavaScript for data-intensive applications to avoid network round trips and request processing overheads. I will now discuss the trust model of the Shredder design. For those who don't know, a trust model identifies the specific mechanisms that are necessary to respond to a specific threat profile. On the next slide, I will discuss the details on how Shredder makes sure this is possible. Here I will tell you the Shredder's intentions to make the trust model. They will sound familiar to the lectures we have heard in class before. Tenants do not share state and cannot communicate through Shredder. The only goal is tenant isolation. Keeping that in mind, it should be obvious no tenant should be able to access another tenant's state. As well, tenants should not be able to access each other's state, and tenants should not be able to access the storage state without going through its storage function-facing interface. As seen in the illustration for the design before, After the request goes to the networking layer, it should go through the storage function layer, and this is where the interface would be. Tenants are the ones who create the functions to store in the function layer, and they can call those functions. Every tenant's code is run in a separate VA context that is associated with that tenant. They are in their own isolated virtual machine. The storage function code interacts with the store through the same get and put interface that remote tenant operations use. This helps ensure the interface itself provides no new avenues for attack by tenants. A very important property is each context is bound to the tenant that installed it. The store never allows operations on records associated with a tenant ID that differs from the context operating on it. This prevents users from trying to manipulate store data that isn't their own. Furthermore, the store only returns views of records to a tenant that were put there by that tenant. This helps with the confidentiality so people cannot see the data stored on someone else's context. The paper further explains that the isolated VA code cannot change the views or manipulate references. Shredder's trusted computing base includes the OS kernel, libraries, and the hardware on top of it which it runs. These are not directly exposed to users, but vulnerabilities in them can still lead to potential exploits. Safety of Shredder is very dependent on V8's isolation of untrusted code, and because of this is very worrisome due to the fact a few vulnerabilities are reported every year. So indeed, Shredder's design has confidentiality risks, especially with more attacks likely to emerge. Now that I went over the Shredder design, Alex will go over the implementation details.
Hi, it's Alex again. I'm going to present some implementation details. The time to move from JavaScript code to the store was 31 nanoseconds. And for comparison, a process context switch takes 2000 nanoseconds. So V8 is pretty quick, and this will increase the throughput, which is a desirable feature, faster processing. Here are some more implementation details that increase throughput. Zero copy data access. All key value pairs stored in Shredder are stored outside of V8 in the storage heap. Local get and put operations are optimized to avoid copying records into and out of storage whenever possible, whereas remote get or put would require moving the records over the network. For some operations that use a few larger chunks of data, Shredder's simple zero-copy get and put interface is efficient, but some data-intensive operations suffer. To solve this, Shredder eliminates control transfer between tenant-provided code and the store for simple read access to records. This uses V8's code stub assembler, which is a low-level intermediate representation very close to assembly language. This is called an exitless get operation. The context is the way V8 organizes a tenant's state and code. Get is implemented entirely with V8 context, so no cross-domain calls are needed. Tenants can't force arbitrary memory accesses through get because get goes through a hash table. Tenants can only access the hash index through get, which can only happen when the tenant's context is executing the supplied CSA code. Tenants cannot overwrite or manipulate the CSA code because V8 doesn't allow code to construct or manipulate pointers. Also, object creation and destruction is known to be costly in V8, so Shredder's CSA-based get allows objects like array buffers to be recycled. Now I'm going to talk about evaluating Shredder's results. One good way to evaluate the results of the paper is to look at comments from other papers in the literature. I found a very recent paper called Phasum Lightweight Isolation for Efficient Stateful Serverless Computing that cites the Shredder paper. And they asked, in reference to the Shredder paper, the following questions. If we use a long-lived VM to maintain state, then do we lose the benefits of serverless computing? They said scaling the virtual machines adds complexity, and asked if we co-locate state and functions on a single host, do we lose out on scale? All of this is about the efficiency of parallel processing using V8, which the authors of the Shredder paper admit is not all that great because V8 is not fully optimized for the ways that they're using it here. They think that with more work, it could be made better, and that parallel processing inefficiency could be smoothed out. In contrast to CPU scalability, the tenant scalability of V8 is good. Number of tenants has almost no impact. Switching between V8 contexts does add a small overhead when you have more than 1,000 tenants, but the server scales well, only about a 6% performance decline. The benefit of Shredder comes from minimizing data movement. In the graph, it shows the result of getting the first value from an array. With a remote get or put, we have to transfer the entire array. With Shredder, we just get the first value on the storage server, and then we can transfer the first value only. So we can see that when the array is not very big over to the left side of the graph, that that overhead from Shredder, mainly the overhead of entering and exiting the V8 context, is big enough that the regular remote get put has the best throughput. But as the array gets bigger, then transferring that array is more costly. And so eventually you get to a point where it's better to do the computation on the storage server through Shredder and just transfer that first value rather than transferring the whole array. The paper also examined particular applications of Shredder. One application was graph algorithms. And one graph algorithm was throughput of a k-hop graph query. A k-hop graph query is a query that, in terms of, say, a Facebook graph, would extend to a social distance of k plus 1, meaning that a one-hop graph query extends to your friends of friends. A two-hop graph query extends to your friends of friends of friends. That's how it's defined. So it says it's orders of magnitude more than a plain key value store, meaning a non-Shredder approach, and it's 3.5 times as good as without CSA or without the optimizations. So a very good performance for this graph algorithm. They also did a neural net application. The performance was not as good. Sometimes Shredder didn't do as well. Sometimes it did a little better. It really stands out with the graph algorithm. Finally, we have related work and conclusions. First, some related work. Shredder takes a different approach to code isolation that eschews conventional hardware-based protection mechanisms. RDMA, or remote directory memory access, reduces overhead at the receiver, but it cannot have application-specific semantics, rendering it useless in solving data shipping problems. Using V8 to isolate code is not a new idea. Node.js is similar. MongoDB also uses JavaScript in databases. Shredder is just more focused on performance. Comet is a decentralized hash table that allows applications to extend it using Lua sandboxed extensions. Like Shredder, extensions also interact with the store through a get-put interface, but it retains a boundary between functions and data. Finally, software fault isolation has long sought low-cost ways to contain untrusted computation, as have some Postgres extensions. Conclusions. While applications can use Shredder as a normal key-value store, they can also embed computation directly next to their data. Shredder achieves millions of tenant-provided functions per second over stored data with remote access latencies of 50 microseconds. And Shredder eliminates movement across the network, between the network card and storage functions, and between storage functions and data. We might even say that Shredder attacks every layer of the storage server.
Thank you for watching our presentation. Leave any comments or questions down below.